This is one of a series of plate tectonics discussing the Australian plate. A rather old diagram of mine illustrating the Australian plate as we have traditionally believed it to be, actually shown here, including India, effectively not including Arabia, although we've moved together with those continents for some time. It's believed today that a new plate boundary is developing from Sumatra across to the mid-Indian Ocean, as shown there in dotted red. And India is effectively excluded from the so-called Indian-Australian plate today. Most of the southern boundaries of the plate, shown in red there, are expanding boundaries where new oceanic crust is being formed. The blue lines are mostly subduction zones. That is where oceanic crust is being destroyed, or in the case of India, if one takes the general plate term, India-Australian plate, and Papua New Guinea, continental crust is colliding with either continental crust to the north or other oceanic material. The Australian plate, we've got there the blue denotes the convergent and transcurrent margins, and red defines divergent plate boundaries. There are also many transfer boundaries amongst those where they're dislocated and showing a jig-jog pattern. The arrows indicate directions of relative movement of the adjacent plates as well as the Australian plate. So there's a slow movement even of the Antarctic plate, only about 10 kilometres every million years, fairly rapid movement of the Pacific plate, and opposed movement of the Australian and Eurasian plates. And of course, there's quite a diverse direction between the Australian plate in the north and the westward movement of the Pacific plate. In previous discussions of plates, particularly Africa, we've outlined how oceanic crust can be dated and that it occurs in almost zebra-like bands on the ocean floor. It's forming today where the red line occurs in the mid-ocean rift between the Australian plate and the Antarctic plate. And this is progressively adding oceanic crust to our plate and to the Antarctic plate. And is the reason we are moving north as a continent. The whole plate is moving from the creation of new crust at the mid-ocean ridge. So we have the yellows there representing perhaps 30 to 50 million years, 60 million years for the olive colour. Some older crust in the Tasman Ocean in the far right, going back 80 million years in that zone there. And likewise, the Indian Ocean has some older crust where it's separated from Australia. The dark green and the grey represent actually unknown age dating, but there's probably crust as old as 100, even 160 million years out between us and Indonesia today. But it's rapidly being subducted beneath the Indonesian arc. We've done before the principle of the spreading of oceanic crust. I think it was a boiling cauldron of jam, and convection currents drag on the bubbly scum of the jam, draw it away, much like that continental fragment shown floating on the central right in yellow. But the syrupy jam comes through to separate the surface scum and push it laterally until such time as the convection currents change in the substrate. And our substrate, the lithosphere, the rocky section of the Earth, is about 100 kilometres thick. And drag on that layer results in the plates being separated and volcanism occurring to add to the oceanic crust. So we have upwelling of basalt at the mid-ocean rift that's driven by gravitational rise of hot magma from convection currents in the Earth's mantle. And as a result of this, a new oceanic crust is formed. So you can see here a situation that existed, say, 45 million years ago, with only a very narrow ocean, rather like the Red Sea today, and a failed rift, rather reminiscent of the Dead Sea Rift, or the one that goes through to the Med Sea along the Suez line, a triple point effectively to the south of Adelaide, but not illustrated very widely. The failed rift that goes through Bass Strait is, of course, responsible for various basins like our Bass Basin or our Torquay Basin, Gippsland Basin, which is where our petroleum supplies are located. And the Tasman Ocean centre line is shown very severely rifted by transformed faults, and that demonstrates that Zealandia moved apart earlier than 45 million years ago, as early as 80 million years ago, and gradually stretched out the crust, represented today by the Norfolk Ridge and the Lord Howe Ridge, rather thin crust attributed to the 8th biggest continent, Zealandia, mostly subsea. So that's an example of the stretched crust where some 80 million years ago, the subduction zone effectively would have been offshore Australia, not far distant from the coastline as we know it today. It has gradually moved eastwards by trench withdrawal or subduction zone withdrawal, and is now way out Suva, Tonga, etc., and the North Island of New Zealand. That's the very pronounced volcanic belt that's recently erupted at Tonga, and it's known as the Kermadec volcanic arc or Kermadec Trench. Pacific Plate is currently moving west-northwest and subducting along that whole belt from the North Island of New Zealand right through to beyond Tonga. The plate boundary, that is the plate boundary of the Australian plate, swinging in an arc coming up through Fiji, turning southward down the Kermadec line, crossing across the South Island as a transfer or transverse fault, basically, with the Australian plate carrying the North Island and the Pacific plate carrying the South Island of New Zealand. And subduction actually changes orientation to the south of the South Island. It's actually the Australian plate, oceanic crust of the Tasman Sea sliding in underneath the Pacific Ocean, the Chatham Rise, and in the north, the subduction is opposite to that. It's the Pacific Ocean crust sliding in under oceanic crust of the Australian plate towards New Caledonia. This is just a cross-section showing the dividing range on the left through to the Lord Howe Rise and the nature of the faulting with exaggerated vertical scale, showing how the crust has been teased apart, like teasing wool apart in effect. And the central oceanic ridge of the Tasman Ocean is shown in red on the lower diagram, with the Lord Howe Rise dotted to the east of it. And the Norfolk Ridge, which extends right down to the North Island of New Zealand, is on the right-hand side of that insert. So separation of Zealandia from the Australian and Antarctic continents effectively started about 85 million years ago. This is a closer version of the complex situation of New Zealand. The North Island is on the Australian plate. It has an unusual situation in that although there's subduction in the Pikarangi Trough of Pacific Ocean crust beneath North Island, as illustrated by the inset, you do have a volcanic arc from the A-dashed point, Ruapehu, etc., through Taupo, the lake. It's obvious there in the centre of the North Island. And it continues up as a volcanic arc all the way up the Kermadec Ridge. But both in North Cape, marked with a C, and East Cape, marked with another C, you have abducted crust. That means the oceanic crust had at one time something of the order of 20 or 19 million years ago. Instead of subducting along that zone, it actually rode up over the continental mass of the North Island, or the section of the North Island, and we have exposed in those areas today oceanic crust, forming high mountainous areas, in fact, in places. Anyway, today you have two opposed subduction belts, one to the west in the north and one to the east in the south of the South Island, which are joined by transfer faults. The main one being the Alpine Fault, with lateral movement of the Australian block north relative to the Pacific plate, which is westward. And it's therefore a sliding fault with some compression, resulting in deformation, mountain ranges, and subsidiary faults, particularly through the Marlborough region, as we see them fanning out into a series of en-echelon structures. That section A-B is illustrated on the right. And mainly we're showing there the subducting plate and the massive faults that occur in the region, say around Nelson and coastal New Zealand. The volcanic belt under A-dashed is where the plate has reached about 100 kilometres in depth, and you therefore get melting of the slab that's descending, due perhaps to the contained water lowering melting temperatures. Magma stringers join to erupt as a series of volcanic centres running from A-dashed, which is Ruapehu, Tongariro, through the enormous eruptions of Taupo and Rotorua to White Island, and extending submarine volcanic edifices. There must be 75 to 100 of them, I would imagine, between there and Tonga, which erupted this year in January 2022. So the Alpine Fault is technically a transverse fault, but because it's a plate boundary called a transfer fault, it's transferring reversed subduction between north and south. And the plates, however, do slide past each other. We say that this type of boundary frequently joins two opposed subduction systems, or maybe two opposed oceanic rises. In Northland, we have the abduction marked by point C, where the Pacific Oceanic crust rests on Australian continental crust, as in the section AB, which I've sketched. A slab coming from the oceanic crust sliding up over the continental crustal material. That Alpine Fault through the south, very clearly shown by the high ground of the eastern side, snow-covered, particularly well illustrated in Fiordland in the south, but quite clearly demonstrated. Subduction starts to take over actually in Fiordland with subduction trench out to sea, and this possibly accounts for the more abrupt ranges in that region and less well-defined margin. And the Alpine Fault of the South Island is a slightly oblique transform or sliding fault. It is the Australian Pacific Plate boundary. And that's illustrated by an inset at the bottom right, so that the Western Plate, Australian Plate, is moving northward, and relative to that, the Pacific Plate is moving west-southwest. So about of autochthons. Autochthons stay in the same place. Allochthons move away, sometimes, well, certainly tens, sometimes hundreds of kilometres, pushed by plate movement across the continental material and become an abducted allochthon. But elsewhere, there's severe deformation in the North Island of New Zealand, deformed, but it's still in place. So that that would be a result of extreme pressures resulting from the subduction or near abduction of the slabs 20 million years ago. Looking again at this Australian plate margin, it's really now teased up so that you've got true ocean in the Tasman Sea. The South Sea Basin has been spreading likewise, as is a ridge between the North, as is a trough between the Norfolk Ridge and the Lord Howe Rise. The area I mentioned before is teased out, rather like taking wool and separating it or thinning it. So you've only got fragments of continental crust, relatively thinned, with oceanic sections between them. The red line demonstrates very clearly the proposed subduction north of North Island to the west, Macquarie Ridge in the south. There's a little bit more abduction actually at Macquarie Island, rather reminiscent of what's occurred in the Northland region. There is a block of the Macquarie Island which has suffered abduction in the past. Chatham Rise, Campbell Plateau are on the Pacific Plate, but plate boundaries have changed, and much of this material, though now rotated, probably has come from Antarctica, which may be covered in the initial discussion on the Antarctic plate. So the Australian plate margin is remarkable for this elongate and prominent kermatic subduction zone in the north. It changes in the south to the Alpine Fault, which is a transverse margin or transfer because it's a plate boundary. It then reverses in sense of subduction in the Macquarie Ridge to the south. Now, this is a view of the active volcanoes in triangles, and the I believe the yellows are large earthquake epicenters. They may be volcanoes that are not known to be active at this stage. I'm not positive of that, although there would be many, many more dormant and extinct volcanoes along that trend as is shown from this inset at the top right. Monowai, you can see it right up. It's still south of Tonga, but looking at the ocean floor there in a side scan view, you can see a very large crater, the central probably emergent intrusive boss. Other volcanoes around it, that would be typical of the entire belt running from Taupo in central New Zealand all the way north to Tonga and beyond. So the subduction situation there is oceanic crust of the Pacific plate against oceanic crust of the Australian plate. So you have island arc with some emergent volcanoes as volcanic islands and sometimes circular reefs or atolls where the cooling volcanoes have gradually subsided, been worn down, or substances occurred as they cooled, and has left a circular reef as the only evidence of the underlying volcano, many of which are as large as Fuji. So the trench is very prominent, and there are some features which are worthy of note in relation to that. And here is one of those. You'll notice the Kermadec Trench extending north from East Cape. But in the top right of this diagram, we have the Lewisville Ridge, which is a whole line of extinct volcanoes, which date from about 75 million years age, since they were eruption centres, to 55 million years further south. And there are a series of these which result from a phenomenon known as a hotspot, which provide a key to the movement of Earth's plates. In this case, clearly the line of volcanoes suggests a plate movement which is only a bit west of north. Whereas if one looks at the entire Pacific, you can track the hotspots, and they'll give us a good idea of the plate movement. They occur at a number of places on Earth, probably 20 or so, and they may have existed in the same place for hundreds of millions of years. They're caused by plumes of heat coming from the outer core, the liquid core of the Earth, and they result in large volcanic eruptions that persist as plates of the Earth, as the plates of the Earth ride over them. And they carry the extinct volcanoes away from their heat source. So they provide this key to plate movement. And we can see here a whole series of them. The Lewisville I've added to this diagram, the Marshalls and Gilbert Islands to the north, emanating or coming from the McDonald Seamount. Easter Islands, the source of another line of islands, which close to it are the Tuamotu, and Hawaii, the most well-studied and prominent one, gives rise to the Hawaiian seamount chain and the Emperor seamounts. And we notice there's a very consistent change in direction of those extinct volcanoes at about 42 million years in each case. And it seems that some significant change in movement of the Earth's plates, particularly the Pacific plate, occurred 42 million years ago. It had previously been travelling just a bit west of north, but today it's travelling just a little bit north of west. And that's a very consistent factor across the oceans. Each ocean has its own study of these hotspot tracks. How does it happen? We've got the hotspot arising from this real outer core of the Earth. It sort of collects as a mass of heat, 100-kilometre depth under the tectonic plate, from which occur a series of intrusions to develop monolithic volcanoes like Hawaii, which is effectively the largest mountain on Earth if you take it from a substrate like the bottom of the sea and compare it with Everest, for example, from the Indian Plain. But the motion of the plate, in this case Hawaii, in the direction of the White Arrow, will take that edifice, that volcano, away from its source heat, and a new volcano will develop. But ultimately, you get a line of extinct volcanoes moving away thousands of kilometres over periods of a few tens to hundreds of millions of years. Well, if we look further at the Australian plate on the western side, Indian Ocean, we have the central ridge coming from the Southern Ocean ridge. Again, it's a spreading ridge. Australia is adding to its oceanic crustal material along that ridge, expanding all the way up effectively to the Gulf of Aden, where it changes to effectively transversal transform structures for the most part, and then to compressional boundaries running around the continent of India, the Himalaya, and through Burma, right around the volcanic arc of Sumatra to Java, etc. And so the northern boundary is compressive and destructive because subduction is going on, and you have loss of oceanic crust in the Java Trench, whereas the southern boundary is constructive, adding more and more plate material. But when we look at this, I know it's an artist's impression and it's 25 years old, but there's a very, very prominent ridge extending from the Bay of Bengal southward some few thousand kilometres west of Western Australia. And that's known as the 90 East Ridge because it's effectively along the 90-degree longitude line. Why is it so? I must also add that here that I've got a white dotted line across the centre of the Indian Ocean, which is many regard as the fracture zone between the Indian plate and the Australian plate today. But for this talk, to a certain extent, I'm embracing both within the Indo-Australian plate. So you have this subduction trench, Java Trench or Sumatra Trench, running around south of Indonesia, in which we're getting recycling of oceanic crust. And this is one reason we see no crust older than 160, 180 million years, and some of it is preserved near the question mark on the far right of the diagram, but soon to disappear under Java by subduction. Why do we have this 90-degree east ridge? Well, again, it's due to a line of extinct volcanoes. It's a little more complex than the Hawaiian situation, but we look at the northern half of this map, we'll find that we have quite an extensive volcanic area central called the Broken Ridge. This is where the central ridge of the Australian Antarctic plate stood 9,500 million years ago. And at some stage, we see successively younger rocks from an age of about 100 million years in India, as you go southward down that line to about 40 million years, 43 million years. Now, India was presumably over that hotspot at about 100 million years ago, or 95 million years ago, and has moved away from it. The hotspot today is actually the Kerguelen Plateau, which is well to the south of the 2,500 kilometres south, 95 million-year-old broken ridge. So here's what has happened is the Australian Antarctic plate boundary has jumped southward from somewhere and continued to expand so that it has put space between the broken ridge, its old position, and the current situation of activity, which one would assume has not actually changed real position on the globe. So there's been northward movement of everything away from the Kerguelen Plateau. This takes a little bit of thinking out and plotting, but it's pretty much the same principle. If you think of a little diagram like that inset, where the plates today are separating from the Antarctic ridge, which is south or to the right of that hotspot. In the past, they were to the north. That central ridge was actually north of the hotspot or very close on it. And some 50 million years or 60 million years ago, it may have jumped. That is, the central ridge may have jumped to the new position, a new position, and it has gradually expanded since then by the formation of new oceanic crust. Think about this, there's a real principle involved. And I'll just read it. The ages of basalt along the 90-degree east ridge suggests that India was over the Kerguelen hotspot 105 million years ago, because there's a basalt mass of that age in eastern India, and that it moved rapidly northward until about 20 million years ago, when collision with Eurasia occurred. Now, that 20 million years is not registered in this series of volcanics. The youngest shown is 43 million years, but of course the ridge has been spreading for some period like that, and it's been confused, although there is a new record to a certain extent around the Kerguelen Plateau of extinct volcanoes at about 69 million years. And they have very, very old eruptives as well, because that has stayed stationary. So there's ages of 95 million years, 110 million years, even 137 million years, which is the oldest volcanism known on the Kerguelen Plateau. Incidentally, that's pretty much the same as basalts in southwest Western Australia on the foreshore at Bunbury. And it's really interesting that possibly means Australia, which is 3,000 kilometres away today, was actually just touching the Kerguelen hotspot well before the separation of Australia and Antarctica 135 million years ago. So reading again, the continuity of the 90-degree ridge indicates that the contiguous Indo-Australian plate moved directly away from the hotspot's position at the broken ridge from 100 million years ago. Since 40 million years ago, a new ridge location for the Australian and Antarctic plates has separated the broken ridge from the active centre of the Kerguelen hotspot. Well, I've quickly gone to a little bit of India. Initially, Tethyan oceans north of India were subducting beneath Eurasia as the Indian or Australian plate with it moved northward. The continental collision about 40 million years ago, the continental mass of Eurasia thrust southward over the Indian plate, and slices of sediment, continental material, and Tethyan ocean crust were ramped southward, creating the Himalayas and the high Tibetan Plateau. This extraordinary mass of crushed material over the very broad Tibetan Plateau and the Himalayan proper. We'll look into that another time, but you can see this crushing's obviously occurred over 400 or 500 kilometres in that central Himalayan domain. And this is illustrated the early subduction of Tethyan oceans underneath Eurasia. They have now entirely disappeared in this region. The Mediterranean, probably the Caspian Sea, are remnants of the Tethyan oceans. So it would have been a bit like Sumatra today, with volcanic island arcs and the mainland of Eurasia behind it. And then with later collision continent to continent, you get this effect that we see in the upper diagram. I think I'll state there, initially, Tethyan oceans north of India were subducting beneath Eurasia as the Indian plate moved northward. With continental collision about 40 million years ago, the continental mass of Eurasia thrust southward over the Indian plate, creating the Himalayas and the high Tibetan Plateau. Now, this is the Australian plate. We can see Australia sitting there, moving north-northeast at something over 60 millimetres per year. That's equivalent to 60 kilometres every million years. And so you can see, ultimately, you can develop something like the Southern Ocean over a period of 65 million years with that rate of lateral movement or northward movement. But the Antarctic plate is actually moving a little bit southward, 10 to 13 millimetres a year, whereas the poor old Sunda plate up in the northeast corner doesn't quite know where to go. Various small platelets are being rotated or pushed in opposing directions by the enormous momentum of the Australian plate moving northward and subducting beneath Java, Sumatra, of the Pacific plate pushing westward into that bulge that we see in Sulawesi. And just one little arrow to the north there, visible on the margin of the diagram, right up in the top corner, showing the westward movement of the Caroline, or perhaps it's the Philippine Sea plate there. So we can see roughly where the 90-degree east line comes down and has no bearing on these new plates that seem to be fracturing in the central Indian Ocean. There's also an old fracture, more or less along the line of the 59-degree mark in the middle. It goes north-south rather than east of north, but it seems to be an entirely new boundary forming, judging from the epicenters of earthquakes that occur out in the Indian Ocean there. Clearly, there's quite a lot of fracturing going on, which has suggested that a plate boundary may develop between the Somali plate and the northern end of Sumatra. And that's roughly coincident with the point where the old suture exists, but I'm sorry, that point is coincident, and that's where the tsunamis of 2004 originated. So we can only say the southern margin of the Australian plate is simple growth of oceanic crust, and that's defined by the parallel bands of increasing age as you come from centre ocean spreading ridge to the continental masses of Antarctica and Australia. So zero age in the middle, 60 million years roughly at the southern Australian border. But if we look at the northern boundary marked out in blue in contrast, which is the subducting boundary, or green, which is the transverse or transfer section running across the section of Papua New Guinea, West Irian. There's an amazing array of dislocation, fracturing. The so-called Sunda block, which is essentially a portion of Eurasia, is broken up into a whole series of microplates. They're not actually defined here, whereas the Pacific, coming in from the west, has broken into larger plates. The yellow one, which is the Caroline plate. The blues are the older ocean crust of the Pacific, dating back 160 to 180 million years, oldest known oceanic crust anywhere. And these are pushing onto the Philippine plate, which is rushing into Philippines and in one zone into Sulawesi. And the eastern side of the plate, as we can see, again, the subduction on the Kermadec Trench reversed to the south of the South Island down to the Macquarie Island, but it then becomes a transform, ultimately joining it with the mid-Pacific rise. Went backwards, unfortunately, no connection here except to show the subduction zone along Java, Sumatra, known as the Java Trench, and illustrated there from a bend above Darwin, which is the Banda Arc, and it results to a certain extent from the transfer fault that slides through the Turkey's head of West Irian, and that's due to the westward movement of those Pacific-related plates. Here then some outlines of those unusual plates and the twisting and deformation that occurs in the region of Timor and Banda Sea. This is by no means the only explanation of this region. It takes ages to sort the way through different concepts. But there are subduction arcs in every direction. Certainly Celebes, or Sulawesi, I beg your pardon, used to be called Celebes, is the centre of very significant subduction in different directions and volcanic arcs that intercept one another. We'll look at those at a later date, but it is a very confusing and complex zone. The Caroline plate moving at 50 millimetres per year. That's 50 kilometres every million years. It's quite significant. That's the effect has to be taken up in these volcanic arcs by some form of deformation. Now, the Java-Sumatra Trench is a simple subduction zone where the Australian plate, is effectively oceanic crust here, and not continental plate so much as marked, but it's the Indo-Australian plate in this region, sliding in because of its increased density as basaltic oceanic crust. It slides in under the continental and volcanic material of Java and Sumatra. There's a little Christmas Island sitting up there. It's a simple form of subduction with very significant associated earthquakes, seismology, or seismicity, I should say. Seismology is the study of them. And when it gets to 100 kilometres depth, you have melting of the subcrustal material, magma rises, and is evident as volcanoes along that line. And the triangles indicate the volcanoes that are active or dormant between Lombok and Sumatra. Don't even think that shows Krakatoa, for goodness sake, in the straits between Sumatra and Java. Suffice to say, there's a little inset area that we would look at in more detail. But Christmas Island and the Trench are quite a few hundred kilometres south of the island mass of Java, because that subducting crust has to get to a depth of 100 kilometres before it generates the magma that will give rise to that volcanic arc extending all the way through that belt and all the way along Sumatra. I won't bother to discuss Wallace Line today, which is the boundary between the Australasian faunas and those of Eurasia. Here's another detail of that area of showing depth of earthquakes. The red ones are the shallowest, green getting to 300 kilometres depth, and the black ones north of the island mass of Java, but continuing up through southern Sumatra, between 300 and 700 kilometres depth. Notice the mass of earthquakes in Sulawesi on the northern boundary. That's taking the brunt of a great deal of deformation today. Some of those boundaries are shown on the lower diagram, again illustrating the active volcanoes. And many active ones in Sulawesi, on the northeast arm of Sulawesi and up through the Philippines, and the Spice Islands to the east. Those typical stratovolcano in Java, they're called stratovolcanoes because they effectively build up strata, you might say. On the flanks, you'll get alternate ash falls and lava flows, which are fairly viscous, don't flow far away from the volcanic edifice, and hence the harder volcanic layers tend to support and to protect the ash, and you get beautiful cone-like shapes developed in stratovolcanoes, which are characteristic of the island arcs and subducting zones around continental margins. Mount St. Helens, for example, in North America, Mount Fuji in Japan. And here's that detailed section of West Java, just showing the volcanic edifices, many of which have been dormant in historic times, but if they've erupted or been shown to have erupted in the last 10,000 years, they're still regarded as an active, potentially active centre. The subducting Australian plate is reflected in lines of volcanoes. Melting or magma results at about 100 kilometres depth, not 100 metres depth, from wet sediments carried down on the subducted oceanic crust, which itself is melted due to lower temperatures, lower melting temperatures induced by included water. Move further on the Australian northern section of the Australian plate. Papua New Guinea has a very strong left-handed transverse fault running through the turkey's head and across the back of the turkey, you might say, sliding along the ranges in the Papua New Guinea, becoming a northward-facing subduction zone as we swing around south of New Britain, Bougainville, and the Solomon Islands. Behind it, there are collapse zones or spreading zones, such as the Woodlark Basin, which has only very recently been expanding in the last 6 million years. Prior to that, the Coral Sea between mainland Australia and the subduction zone expanded significantly in the region about 55 to 60 million years ago. Solomon Sea a little more recently, something like 30 million years ago. And more basins are subsiding in the region of the Banda Arc currently, and also in the North Banda Sea Basin between 7 and 13 million years ago, relatively recent, as distinct from crustal activity that's going on today as a result of all these faults moving due to the western passage of the Pacific Plate and the northern passage of the Australian Plate. And the northern margin then is complex due to the collision of three major plates, Australian, Pacific, and Eurasian plates. The result is a series of microplates with some sliding under or subducting and other locally riding over another or abducting. Others slide past one another, resulting in transverse faults, which act like the San Andreas or the Alpine Fault in New Zealand. And you can imagine the same thing happens in pack ice at the bow of a ship. As it forces its way, you get abducted slabs, is in Sulawesi, where you have very prominent transverse faults translating opposed directions of subduction and resulting volcanism, very extensive in northeast Sulawesi and extending up into the Philippines, where there is opposed subduction running up through the southern Mindanao. The main Sunda Trench, otherwise Java Sumatra Trench, is shown in the south, and lines of little red triangles are the active volcanoes in Java and the Banda Isles, running around to Seram, where the arcuate character is the result of the presumably westward thrust of the Pacific-related plates. Timor is a complex isle. We'll discuss that on some occasion. It's riding a bit like a surfboard on the accumulating wedge or accretionary wedge of the subduction zone to the south. It's even more complex as we get nearer to the main Pacific Plate. The Caroline Plate has broken off from the Pacific, as has the Philippine Plate to the north of it. So too these microplates against continental Australia, which effectively in this case is Papua New Guinea. We get abducted crust, abducted oceanic crust, where those dark grey pieces are illustrated. We get rotated plates such as the South Bismarck Plate. There's volcanism, there's subduction, and there's all sorts of complexity. Newly subsiding basins like the Woodlark Basin off the tip of PNG. So the plates are constantly moving, rotating, and changing shape. It's not so much an area of growth of continental plate or growth of oceanic plate. It's a zone of, rather than a dilation, it's compression, and hence not much in the way of new ocean forming, except the Woodlark Plate, but fold belts and mobile or orogenic zones develop where continents meet, and the subduction zones or abduction of oceanic crust occurs. It's a very complex story to the north of Australia. And here it is illustrated by earthquake epicenters, showing Philippine Plate subducting under the Philippines, and the Australian Plate effectively subducting under Indonesia, or likewise from PNG right through to Fiji, subducting northward under the Pacific Plate, which is moving westward. Just a study, and we ask in and around Sulawesi. On our eastern margin, we're getting back to see the Kermadec Trench extending south to New Zealand, and the Fiji belt is an accurate subduction zone, as we saw in the last diagram. The extrapolated or extended crust of the Zealandian continent, mostly submarine, having been teased out from southern Australia and Antarctica over the last 100 million years. So looking again generally at the overall Australian plate, the Indian plate being disregarded here, we can see though its boundary is taken as roughly Aceh, where the earthquake epicenter occurred that resulted in the tsunami of 2004, and it stretches westerly towards the Somalian plate and the central ridge of the Indian Ocean. And that southwest or southeast Indian ridge extends all the way down, separating the Australian plate from the Antarctic plate to the south of Macquarie Island, where it turns north again, partly as transfer fault, till the subduction zones easterly, then westerly as you cross New Zealand. Goes into that mess of interaction between the westward Pacific plate and the northward Australian plate as we traverse along that northern boundary. There are zones of active faulting within the Indian Ocean, marked there as the 90 East Sumatran orogeny. Examine this plate using the colour guide, red for divergent boundaries, blue for converging subduction zones, as is red, divergent, I beg your pardon. Green is the transform plate boundary that often joins these. And the arrows are given as movements relative to a fixed Africa. So I think just a few moments looking at that diagram will probably close our discussion today.